Hey everyone, and welcome. Today, we're going to do something kind of cool. We're going to make the invisible visible. Yep, we're diving headfirst into one of those huge ideas in physics, something that controls literally everything, from a planet zipping around the sun all the way down to that book just sitting there on your desk.
I mean, it sounds like a simple question, doesn't it? But honestly, this question is the key to, well, everything we're about to get into. The answer? It's all about the pushes and pulls that are constantly happening all around us every single second. So yeah, let's get right into it.
Okay, so to really tackle that big question, we have to start at the very beginning with the most basic building block of motion. Before we can even think about drawing diagrams, we've got to get a handle on what a force actually is.
And you know what? At its heart, it's super simple. A force is just a push or a pull. That's it. Think about it. It's the kick that makes a soccer ball soar. It's you lifting a heavy bag of groceries, or even the wind pushing on a boat's sail. It's always about one object interacting with another.
So what's the point of these pushes and pulls? What do they do? Well, they're basically the agents of change in the universe. A force can make something speed up, it can slow something down, it can bring a moving object to a dead stop, or it can just nudge it in a new direction. And this is huge. Without a net force, an object's motion just stays the same. It keeps doing what it was doing.
Now, we can pretty much split all forces into two big groups. First up, you've got your contact forces. This is the obvious stuff, right? Where things actually have to touch, like you pushing a box. But then you get the really weird ones, the non-contact forces. These guys can act across empty space. Gravity is the classic example. I mean, the Earth is pulling you down right this second, but it's not physically touching you.
All right, so we get what a force is. A push or a pull. Simple enough. But here's the problem. They're invisible. So how on earth are we supposed to work with them? How can we figure out what's going to happen when you've got a bunch of different forces all pushing and pulling at once? We need a tool. We need some way to actually see them.
And this right here, this is absolutely crucial. Think about it. If I ask you to help me push a car, it's not enough for me to just say, push really hard. You'd immediately ask, which way? See? You need to know both the strength, we call that the magnitude, and the direction. They're both equally important parts of the story.
So the tool that physicists came up with to visualize this it's brilliant in its simplicity. It's the vector. And a vector is really just a fancy word for an arrow. That's it. The longer the arrow, the stronger the force. And whichever way the head arrow is pointing, well, that's the direction of the force. And just like that, we can see the invisible.
Okay, that's great for one force. But let's be real. In the real world, things are way messier. It's almost never just one single force acting on something. Usually, you've got a whole bunch of forces all competing with each other. So, what do we do then?
Yeah, this is the million-dollar question, right? How do we figure out the grand total effect when an object is getting shoved and yanked in all these different directions at the same time? Imagine a crazy game of tug-of-war, but with like 3 or 4 teams all pulling in different directions. You can't just add up how strong each team is. You have to factor in which way they're pulling. Well, the method for figuring this out is actually kind of fun and way simpler than you might think. It's called the head-to-tail method. All you do is draw your first force arrow. Then you go to the tip of that arrow, its head, and you start drawing the tail of your second arrow from there. You just keep linking them up like a chain, connecting the head of one to the tail of the next. So once you've made this big chain of all your little force arrows, there's just one last thing to do. We need to find the one single force that sums up the whole shebang.
And that special arrow has a name. It's the resultant force. And finding it is super easy. You just draw a brand new arrow that starts all the way back at the beginning, at the tail of your very first vector, and ends at the very tip of your very last vector. That one new arrow, that tells you everything. It's the grand total, the final outcome of all those other forces combined. It's the net effect.
Okay, let's make this real. Picture this. You're trying to drag a heavy brick across the ground with a rope. You're pulling, right? So that's one force. But wait, there is another force fighting you every step of the way. Friction. That scraping feeling between the brick and the ground. So, like it says here, not all the muscle you're putting into it is actually used to move the brick forward. And here's the big takeaway from that. When you do the head-to-tail thing with your pulling arrow and the friction arrow pointing the other way, the final resultant force, the arrow that shows how the brick actually moves, is going to be shorter. It's weaker than the force you're putting in. Why? Because some of your hard work is getting canceled out by that pesky friction.
Here's another cool example. Let's say 2 people are pushing a brick.
One person pushes it from the west, so they're pushing it east. The other person pushes it from the south, so they're pushing it north. Now what happens? Does the brick go east for a bit and then north? No way. If we draw our vectors head to tail, that final resultant arrow points diagonally to the northeast. A totally new direction is created just by combining the two.
Okay, now for what I think is the coolest part of all this. What happens when the forces aren't just competing? What happens when they're in a perfect standoff, when they totally and completely cancel each other out?
The classic book on a table is the perfect way to think about this. I mean, look at it. It just looks still. Peaceful, right? But what's really happening is that the book is the center of an epic, invisible tug of war. It's not that there aren't any forces acting on it. Oh no, it's that the forces are in a perfect stalemate.
So, who are the two opponents in this fight? Well, first you have gravity, constantly pulling the book straight down. That's its weight. But at the exact same moment, the table is fighting back, pushing straight up on the book with the exact same amount of strength. And that upward push from a surface has a special name. We call it the normal force. So what do you get when you have a pull down and an equal and opposite push up? Think about our head to tail method. You draw the down arrow for gravity. Then you start from its tip and draw the up arrow for the normal force. And where do you end up? Right back where you started. Your final resultant arrow would have 0 length. The resultant force is 0. Nada.
And that, my friends, is the whole secret. When that resultant force is 0, we say the forces are balanced. And balanced forces mean no change in motion. It's such a cool idea. Stillness isn't caused by a lack of forces, it's caused by a perfect balance of forces. All right, I'm going to leave you with a little puzzle to chew on. Picture a car driving down a perfectly straight highway at a steady 60 miles per hour. It's moving, for sure, but its speed isn't changing, and its direction isn't changing. Its motion isn't changing. So, based on everything we just talked about, are the forces on that car balanced? What do you think the resultant force is? Something to think about. Thanks so much for joining me.